Okay, so we have seen the differences between the true error and relative error, and also approximation error. Now, we are dealing with the numbers, and certainly we need to know how a computer evaluates a number. In fact, in our daily life, we are using decimal system in general because that's much more easier for us to understand. And so in decimal system you have ones, tens, hundreds, thousands, 10,000s, and it goes like this. So certainly each uh, digit can be represented by a number from 1 to 8, as is the case in abacus. Now let's see how we can decompose a number in a decimal system first. So just consider a number 86,409. So in the ones we have 9, in the tens we have 0, in the 100s we have 4, in the 1000s we have 6, and in the 10,000s we have 8. And certainly multiplication of each number with the corresponding value and gives us another number. And if we sum up them, we arrive at the number that we are interested in, the final number that we are interested in. And we use the same idea in computers, but the structure of the computers are different. So how different they are? Now the point is this. Computers are actually complicated machines. And as is the case in the first computers or calculators, they can only observe whether there is something or not. So basically we are talking about a whole or something. So there is something or there is something not. Or in other words, there is a hill or a whole. Okay, now hills corresponds to 1 and whole corresponds to 0. So we have two options. Therefore, for a computer or computational system, it is much more logical to use a binary system, which depends on only two numbers. Each of these units are called bits. Okay, so when you have a system with 8 hills and holes, so you have an 8-bit system. And 8-bit is 1 byte. So 1 byte is made of 8 bits. And this is how we represent a number. So let's look at the number system. Therefore, it is much more logical to use the binary system because you can only define two values in that system. And analogous to the decimal system, we have different digits. So, but in this case, instead of having the values from 10 to the power 0 to 10 to the power 7, now since we are using a binary system, it is from 2 to the power 0 to the 2 to the power 7. Of course, this defines the largest number that we can define in a computer. So this is the number that corresponds to in decimal system. So if you have a 8-bit system, the maximum value that you can define is 255. Okay, so this is the largest number that you can define in a binary system. And of course, the smallest value is 0. Now, the largest number defines the minimum number, smallest rational number, because you divide 1 by 255. And therefore, the smallest number that you can define in an 8-bit system is 0.00392, and it goes like this. This is the smallest number that you can define. Smallest rational number that you can define. Of course, we use different tricks, and we are going to see them in order to handle much larger numbers and negative numbers and so forth. And there's another thing that you need to know. Now, in computers, there are only 3 operations defined. So these 3 operations are summation, subtraction, and multiplication. Division is not defined in a computer processor. Okay, so basically division is done by subtraction. Okay, so this is what 7-bit means. Also, this has an influence, because if you are using a control card in order to control an elevator, and if you need the precision, okay, so this is the smallest value that you can define the range. For example, just think that you have a servo motor. Okay, you want to drive a servo motor. Now, the RPM is controlled basically by the voltage level, because you send square waves. Okay, if it's an AC servo, so you send a square wave which varies from 0 to 10, and 10 means that it will work on a rated RPM. If it is 3000 RPM, if you send the signal pulse, a square pulse at 10 volts, then it gives you 3000 RPM. Now, you want to control this RPM by using this pulse. So what you do is, for example, if you want to run the servo with 1500 RPM, then you should send 5 volts to it. So, in fact, the driver card controls the servo, right? You control it. And the control card has a processor on it. Now, here the story comes. If it has an 8-bit processor on it, this means that the smallest RPM is 3000 multiplied by this value. So this is why you need a higher processors with 16 bits, 12 bits, or 24, 64 bits. So this is what bit means. So you increase the precision. Of course, we do tricks, and what are those tricks then? Let's see it. Okay, now just take a number, arbitrary number, okay, in the binary system. So 1, 0, 1, 0, 1, 1, 0, 1. Okay, so, and let's see how we calculate the value for this of this number, which is given in the binary system. So it is 1 multiplied by 1, 1, 0 multiplied by 2, 2 to the power 1, it is 0, 1 multiplied by 2 to the power 2, it is 4, 1 multiplied by 2 to the power 3, it is 8, and then we have a sequence of numbers, and the summation gives us the value in decimal system. So that is 173. Okay, so these are the numbers, but there is a trick that we can do. Now we can define much larger numbers. How we do it? We allocate certain bits for the for different things. So, for example, it depends on the architecture. Of course, here you need to know whether your system the architecture, the computer that you use, the architecture of the computer that you are using has this structure or not. But this is very general. I mean, many of the architectures are using such kind of a system. So the first bit is used for the sign. Now, if you have an 8-bit system, now you lose 1 bit for the sign, but now you can define the negative numbers. So 1 corresponds to a negative value and 0 corresponds to a positive value. Now, the second thing is certain amounts of bits can be used for the exponent, because you can define a number as mantissa multiplied by the base multiplied by an exponent. Again, in the sign exponent region, you use 1 bit for the sign again, of course. Then you have the mantissa for the rest. You can use the rest of the bits for the mantissa. So this is one trick that we can do, but of course this introduces additional difficulties. So what are those? Now just consider a number. Okay, so 1 divided by 34. So this is the actual number, 0.029411765, and it goes like this. Of course, we can write this number in decimal system like this, because we have a certain number of bits and we have to cut it. So 0.0294, 10 to the power 0. And the better is, we can write the same number in an exponential form like this, 0.2941 multiplied by 10 to the power minus 1. Now, this is how we define it, because the first bit is for the sign and we have a positive number, therefore it is 0. Now we have the exponent of the number, so sign of the exponent is the second bit and we have negative here. It can be positive as well, so no problem about that. So it can be 0 as well. Then we allocate 2 bits for the value of the exponent. Okay, so we have 2 to the power 1 and 2 to the power 0 for the sign of the exponent. Okay, and then we go like this, 2 to the power minus 1, 2 to the power minus 2, and 2 to the power minus 3. So this is the magnitude of the mantissa. Now let's look at the value. Now this is my number in binary system. Okay, now certainly I have 1 here, so 1 multiplied by 2 to the power 1, and 1 here, 1 multiplied by 2 to the power 0, and my exponent is 3. Now sign of my exponent is minus, as you see here, so I have 2 to the power minus 3 in binary system. I'm talking about the binary system. Now this results in, now let's look at the magnitude of the mantissa. So what is the value that it corresponds? So 1, 2 to the power minus 1, 0, 2 to the power minus 2, 0, 2 to the power minus 3. And this corresponds to 0.5. So it is basically 0.5 multiplied by 2 to the power minus 3. And the value that I have for this number is 0.0625. Now let's increase the value step by step. So what shall be the next largest number? Of course, the next largest number will come by increasing the mantissa, right? Now the first bit here can be 1, so this will be the next larger number. next number bigger than the previous one. Now I can calculate it in a similar fashion, right? It is 1 2 to the power minus 1, 0 multiplied by 2 to the power minus 2, 1 multiplied by 2 to the power minus 3, multiplied by 2 to the power minus 3, and I will get this number in decimal system. You see, 10 here shows me that this is in decimal system, so 0.078125 will be the next bigger number. Now let me increase the value one more. Now, of course, the first bit can be 0 and then the second bit will be 1, right? This will be the second bigger number. And the value that I have will be then 0.093750. And the next one is the last one, so it's 1. And it goes like this, okay? 0.19375. And it continues like this. So you see, even if I increase the number in a step-by-step manner in binary system, in decimal system, the number increases in a discrete way. There are gaps between the number, for example, 0.0625 and this number. Okay, now this basically means that now I haven't changed the exponent yet, but this basically means that the difference between the two numbers is the delta. The system has a discreteness, or the gap between two numbers, as 0.015625. Okay, and the values between these two are not cannot be defined in a computer. Of course, I can increase the mantissa, so the next bigger number will be like this, right? So remember that this is a minus sign, so it is 1 1, therefore the next bigger number is 1 0 here. So this can be 1 and this can be 0. So as a result, the number will be 1 2 to the power minus 1, 0 2 to the power minus 2, 0 multiplied by 2 to the power minus 3 multiplied by 2 to the power minus 2, and it gives me 0.125 again. Okay, so this is the case. So we have a discrete system of numbers. Now I have two types of errors then, chopping and rounding, because the numbers between them are not defined. I can only define numbers at this point, x, x plus delta x, and x minus delta x. And since I can only define these numbers, so I have to chop some of the numbers. So some of the numbers are not defined precisely. This is basically called chopping. So therefore what I do is I only define the value at this point because of the limited number of the bits. Second thing is the rounding. Now the values here and here are defined as if they are x. Okay, so then you have the rounding error because they are automatically associated with the value at this point by the computer. Now what is the problem? Of course, this is called rounding and round-off errors. There exist two extreme cases, which is in the limiting case of 0 and in the extreme large. Now, if you define a value which cannot be defined higher than, which cannot be defined by your system, a very large number. So I'm talking about an exponent with positive and positive number. Then, depending on the architecture of your computer, that number is defined as overflow because that value cannot be defined in your system. Even with the exponential type of defining the number. Okay, and the thing is, you have an underflow hole here. So you can be very close to zero, a very small number, but certainly your system, okay, because there is a limit that you can define. For example, in this system, let's see what is the smallest number that you can define. So this is 0, right? This is 1, 1, 1. And let's assume that the mantissa is 0, 0, 1. Right? So this will be the smallest number that you can define, smallest positive number. And the numbers below this is and can be assumed as underflow. So if you divide a number to that number, which is smaller than this value, will be considered as division by 0, and will give you, the computer will give you an underflow error automatically. So this is the second type of error that you face with when you are dealing with the computers. Okay, these are the two different type of errors. So you can evaluate the chopping error. So delta x divided by the x. So x is the nominal or actual value of the number, and delta x is the increment between the two values in a computer system, is considered as the chopping error. And since rounding error is half of it, because numbers there are chopped, and the rounding is just any value between these two numbers are associated to the closest value, and the chopping error is considered as epsilon by 2. Rounding error is considered as epsilon divided by 2. Okay, now this means that there is a very small number that you can define in a computer. This is called machine epsilon. Okay, so what is the machine epsilon? Because we know from mathematics epsilon is a very small number, but what is very small? That is the point, and we need to know about it in a computer system. Certainly you have an error, and this error can be defined as base to the power of something. And in this case, it is 1 minus t. Now, t is the significant digits in the mantissa. So that is the that is called the machine epsilon in this case. Okay, let's continue. So now we have seen the round off and errors, true value, true error, approximated error, and so forth. But let's see another thing. We are making an approximation. Okay, and the thing is, we use different tools in approximating something. Generally, we have continuous functions, right? And we have seen something, Taylor series in mathematics. Now, if your function is continuous, you can define any function by using Taylor series approximation as soon as you take infinite number of terms. Okay. So what is the Taylor series? Let me remind you what the Taylor series is. So basically, we write a function by means of its derivatives at a point. And x minus a is the distance of the point, the distance of a point to the reference point. And then we have some terms here. So the square of the distance, the cube of the distance, and it goes like this. Here n is the n in parentheses means that it is the nth derivative. Certainly, as soon as you take infinite number of terms, you arrive at f of x. But it's highly probable that you cannot do it, and you just take finite number of terms, and as a result, the remaining terms are called remainder. Here we show it with Rn. So what is the value of Rn? Rn is from a to x, x minus t to the power n divided by n factorial fn plus t dt. So this is the integral of this function. So this is the remainder terms. Now, how we obtain this remainder? Because this remainder is associated with the error that we make while approximating a function. Okay, we want to approximate a function, and the remainder is directly the error that we made in approximating that function. So first, we have two theorems, and the one is the first theorem of mean integrals. So what's it? Let's read it. If the function g is continuous and integrable on an interval containing a and x, then there exists a point psi between a and x such that a to x gt dt is equal to g psi multiplied by x minus a. Now let's say that x is greater than a, and I want to integrate a function gt. Therefore, I can take a value, an arbitrary value. It may be different, but certainly there exists one point. And if you multiply the value of the function with the distance between the bounds of that interval, it will give you the value of the integral itself. Well, remember that we use method of squares for numerical integration, or we will learn it, how we do it. We will use this theorem also for integration purposes. What else? Now there is another theorem, second theorem of mean integrals. Now in this case, we have two functions, okay, g of t and h of t, or g of x and h of x. Certainly these functions are defined between a and x, and they have to be continuous and integrable. So continuous, I think you already have the sense, but what is integrable? Certainly there is no you can apply any theorem of integration. So this is what integrable means. Okay, for example, a discontinuous function can be integrable, right? You can integrate a step function within an interval. So what it says, the second theorem of mean integral, this integral is equal to g of psi multiplied by integral of the function. Again, the value can be somewhere, it has to be somewhere between a and x. This is what the theorem says us. And by using these two theorems, we obtain the remainder. Now, we have a discrete system, right? We are working on a discrete system. And of course, since we have discrete numbers in a computer, our approximations are discrete as well. So I calculate the values of the function at discrete points. and I can approximate a function by using Taylor series. Now, just think that I have a sequence of points xi plus 1, xi minus 1, and so forth. If I only take the first term, this is called zero order approximation. Remember the example that we have solved, right? Now, if I take the first term and the second term in the Taylor series, so you have the first order derivative now of f of x at point xi. This is called first order approximation. And then I continue. I can take the second term, as you see here. This is the second term. So f of xi plus f prime xi, xi plus 1 minus xi, and plus the second derivative of f divided by 2 factorial multiplied by xi plus 1 minus xi square. So this is the second order approximation, and be aware that you need to take infinite number of terms, and the remaining terms are your errors, truncation errors. You can calculate the nth order approximation as well. Then this will be your nth order approximation, and then you have the remainder. Remainder can be written as like this, okay, by using the first and second theorem on integrals. So here this value is the value between xi plus 1 and xi, because you are making an integration between these two, okay? First mean theorem and the second mean theorem. Okay, now I can write the Taylor series approximation in a different way. Now remember that I'm working on discrete points. Therefore, instead of defining certain values associated with the points, in order not to keep every number in the memory, because every number in the memory will dump your memory, and I want to use a smaller amount of memory in general. This is my objective in coding, in writing, in solving a problem. I want to use less amount of source. So I define a step size, h, xi plus 1 minus xi, because the numbers are evenly spaced. So the space between the two numbers are constant. They do not change in general, at least for a computer. Now I can define the error, right, by means of step size, depending on the where I cut the term. Now I can say that now the truncation error that I made is on the order of, here O means that on the order of h to the power n plus 1. Now remember that here h is your chopping error in a computer system. It can be, I mean, if this is your step size. Of course, you can choose a larger step size in approximating a function, but you cannot define a smaller step size than the chopping error. Then this means that this is the order of your error, and this is your truncation error in approximating a function. Okay, now let's look at a problem. So we are given a function here, as you see. Now it is told us that use 0 through 4th order Taylor series expansions to approximate the function. from xi is equal to 0 with h is equal to 1. So our initial point is 0 and the step size, so we will expand the Taylor series around 0 and the step size will be 1. That is, the predict the function's value at xi plus 1 is equal to 1. Okay, so let's have a look. Now we have f1. This is the function that we have, and f of 1 is 0.2. Okay, this is the true value. Now the approximated value, when we use the zero order term, it's 1.2. And the true error is then minus 1. As you see, it's 0.2 minus 1.2 and it's minus 1. Now let's calculate the first derivative. F prime 0. That's equal to minus 0.4 multiplied by 0.0, because we are expanding it around 0 to the power 3, minus 0.45, 0.0 to the power 2, minus 100, minus 0.25. So the derivative of the function at 0 is minus 0.25. Okay, so this is the derivative. I want to calculate the zero order term. So the approximation is the zero order term plus first order term, and first order term is minus 0.5 divided by 1 multiplied by the step size, and as a result my first order approximation is 0.95. Now I'm getting closer to the number, the actual number. Remember that the first number is 0.2 and now the second number is 0.95, and the true error is minus 0.75. Continue further. Now let's see the second influence of the second order term. First I will calculate the second order derivative at point 0, and this is the actual value, it's minus 1. Then I put it into the Taylor series approximation. Now even though the second derivative is minus 1, be aware that we have to divide it by 2. As a result, I have minus 0.5 here, so it is 1.2 minus 0.25h minus 0.5h to the power 2. Therefore, f of 1 is 0.45. Now it oscillates. And truncation error is minus 0.25. And it goes like this. I mean, if you take the fourth order term, you arrive at this function, f of x for h. Now, the fifth derivative of the function is 0, right? It's a polynomial, fourth order polynomial, and as a result, the fifth derivative is 0. Therefore, the remainder term, the truncation error, when you take all the four terms, you have 0. And f of 1 is 0.2. Okay. And here we see how it graphically changes. So this is the zero order term. You see, it is a constant line at the point 0 where you begin. And when you take the first order term, then you have a straight line. So you define the points between these two as if they are lying on a line. And if you take the second order term, then you have the parabola. You see? So this is how you approximate the function then. So the zero order term is just a straight line, approximating a function as a straight line. First order term is just approximating any function as a straight line, and the second order term is just approximating any function as a parabola. Okay, now let's focus on a trigonometric function. Use Taylor series expansions with n 0 to 6 to approximate f of x cos x at xi plus 1 p divided by 3 on the basis of the value of fx and its derivative at xi p divided by 4. Note that this means that h is equal to p divided by 3 minus p divided by 4, so the step size is p divided by 12. So let's calculate the true value at p divided by 3. So it is 0.5. Okay. Because it is 60 degrees. And when we calculate the zero order term, it is cosine p divided by 4. So p divided by 4 is 45 degrees. And as a result, this is the approximated value. Therefore, the relative true error is minus 41.4%. We can easily calculate it. Now, let's calculate the first order approximation. Again, we have the function itself at the initial point. And then we take the first derivative. So derivative of a cosine is minus sine. Therefore, we evaluate it there. And then we multiply it with the step size. And this is the value of the function, 0.521986659, and it goes like this. Therefore, the relative fractional error is minus 4.4, as you see. And finally, we can calculate it like this. The better is to take the derivatives first and make a table on derivatives. Now, it is asked us to calculate the up to sixth order, right? So the zero order term, first order, second order, fifth order, sixth order, and so on. So the zeroth derivative of an f of x is cos x, and the first derivative is minus sine x. If we take the derivative of minus sine x, it is minus cosine x. If we take the derivative of this minus cosine x, it is sine x. Cos x minus sine x minus cos x, cosine x, and it goes like this. And if we evaluate these Taylor series approximations at these points, it is 0.07, 106, 0.52, 0. Look, the second order approximation 0.977. Now it is 0.499, 0.5000. There are 4 zeros, 7551, and then we have 5 zeros here, 304, and then we have 9s. Of course, we have very small amount of error. And if we look at the relative true error, relative fractional true error, it begins with 51.4%, and suddenly it decreases 4.4, then it is 0.44, and at each time you have at least 1 order of magnitude lower error at each step by just taking one more term to the Taylor series expansion. So you increase the accuracy and you make much more precise computations as you increase the number of terms in approximating a function. Okay,